So in this video, we'll be discussing about the second chapter of Razavi. We will be going with each and every concept, elaborate them and do the simulation parallelly. Coming to this overview of this chapter where basics and the second order effects of the MOSFET will be discussed. So first we'll see the basics and we'll simulate the basics and we'll see the second order effects. Also we do the simulation in the Cadence Virtuoso. So coming to the basic concepts of MOSFET, let me show you. Yes. So this is 2.1 figure, 2.21 figure in the second chapter. This is the circuit diagram they gave. From the circuit diagram, they wanted to simulate the GM variations with respect to VDS. So we'll see that how VDS changes affect the GM, transconductance of the transistor. So let me take my test bench on the Cadence Virtuoso. So this is the same schematic where I took the transistor and connected the transistor with the width of 5 micro and the length of L taken as a parameter, and VDS will be applied at the drain terminal, VGS is applied at the gate terminal. So simple setup. For the simple setup, I'm taking my simulations as S. So VGS is the one parameter, IDC is the one parameter. Basically, this IDC we didn't take. I have to remove. There's no need. So this is also not taken. VDS is the one parameter. Length is the one parameter. So now I will be simulating for 1 micro in the initial case. First of all, what I do is I will be taking the expressions. Let me remove all of them. To make it more clear, let me close this one. Let me create another maestro where I will be doing the simulation once again. So where my schematic, let me take my schematic, let me take, and I'll be launching the AD Explorer, create new, okay, GM variations 1, maestro view. Yes. So here I will be trying to do the simulation. Let me do the setup for the simulation. So analysis type is DC, and operating point I have to save, and component parameter I have to take the component of VDS, where the analysis is DC and taking this component. So automatically my x-axis will set as x-axis will set as VDS. So exactly the VDS is the x-axis. That's what we are expecting. So that's why I'm choosing the VDS, the drain voltage source on the x-axis. So this is how the V3 component is selected, and I'm taking the x-axis from 0 voltage to 1.8 volts. And if it's required, you can keep the linear steps where how many steps are required. Step size I'm keeping as 0.01. So if you don't give also, it will take default values, so no need to worry. So coming to this one, x-axis is set, then we have to bring all the parameters. So copy from all the parameters. The length of the transistor, let me choose it as 1 micro. As we know that in the last video we discussed, as the length of the device is very high, it will be having linear characteristics with respect to VGS change. We can have the characteristics dependency on the gate will be more, second order effects will be less. So we'll be taking that length equal to 1 once. Then we'll see that after length value is reduced, how the second order effects will be more, and what complications we'll get. We'll clearly see it in the next simulations. So let me take 1 micro and the VDS equal to 1.8 and the VGS. So I will be taking 0.6 comma 0.8 7 0.8. So three values I'm taking. So for the different values of VGS, I have wanted to observe the different graphs. So here one graph is given. Let us take one graph initially for the 0.6. Let us take the one graph. So with respect to the VGS equal to 0.6, so we'll be observing this plot first. So before we observe that plot, instead of plotting the GM graph, so let me plot the graph of ID. So let me take the probe and let me take it as a signal, and the signal at drain current. So this is the plot. Let me simulate, and VGS value 0.6. And where across the setup I have to provide the model files. So 90 nanometer technology model files NN is provided, so that is okay, and I can do the simulation. Yes, I got ID versus VDS. So here ID versus VGS we got it, but we have to plot GM versus VDS. So now what we do is we'll be taking that operating point of the GM. So now instead of the current, I have to take the expression GM. So let me go with the expression GM. So let us go with the expression GM. So here let me go with the calculator and let me go with the operating point and let me select my transistor and let me take the parameter of GM. So this is the operating point of the GM will be brought into the window, a master window, and here the expression for the GM is plotted on the y-axis. This is the x-axis, this will be the y-axis. That's what we are expecting actually, right? So after I do the simulation, I will be getting a problem as, yes, even I am trying to get the values of GM, but the GM multiple values we are not getting, only one value at that operating point itself we got it, because we took the expression as GM operating point. So at one point it will be simulated and it's showing multiple values we couldn't get, but the multiple values of the drain current that has a signal which was plotted, and you able to see it. So that waveform you able to see it. So now what we are expecting is, so how exactly ID changes with respect to VDS changes, we have to make sure that the same kind of graph for the GM changes also we are expecting. So for that, there is a procedure, let us follow that. So what we do is, so we'll be going with uh, operating points, we'll save it over here in the folder. So where I'm doing the project, this is the location, this is the drive where I have to create a empty file with the extension, whatever the name that you wanted to prefer, that's your wish, but with the extension SCS, Spectre circuit simulation file, Spectre circuit simulation file, save my operating OP. Yes. So this is the name that I'm trying to prefer for this empty file. And what I do is I will be saving all the parameters of nm naught. What is nm naught? Nm naught is nothing but the transistor which I have, that name of the transistor that I have. Nm naught, the name of the transistor that I have. So that I will be saving. Yes, let me save it and close this one. And now while you are simulating, you have to make sure the setup over here to be ready with adding the definition file over here as that one. So you browse this one on the desktop where basic library that I'm creating for all the basics of MOSFET second chapter, where I'm trying to create all the files in this library. And here I have created save operating point of SES. Just let me open and give it OK. Now you do the simulation. Now you do the simulation once again. And now what we do is we'll be going with the result browser. and where you elaborate this one, you have the DC operating point and multiple set of for operating points you can observe over here. So these and all parameters where you are expecting GM. So here the GM, NM not GM, transistor transconductance value. You can take this one into the calculator and you can take the get data. You can get the data of all the operating points of the GM. So with respect to changes of the VDS, so you can take the data and you can bring into the simulation window. Now we are trying to plot this one. So now if you do the simulation, instead of one point, you can get the multiple points that you can see it on the y-axis with respect to changes of the VDS. So this is how we can do the simulation where the signal with respect to VDS change and the parameter ID, parameter GM with respect to VDS change. So once you do the simulation, now what I'm expecting is, so this is the graph I'm expecting. There is a VDS change with respect to VDS change. The GM, if it is changed, now as per the textbook, we have to simulate these curves where, yes. So the transconductance of the amplifier, transconductance of the MOSFET. As we know, the transconductance of the MOSFET is nothing but the variations of the VGS, So here you change the VGS. There is a change of ID. There is a change of the ID. At what factor the ID change you can observe, that will be defined by the GM. So now how the GM is going to be defined, where with respect to simulation, the GM will be changed linearly. GM will be changed linearly after particular point. Once the transistor is entering into the saturation region, GM will be constant. So this is what the simulation where it is shown in the example 2.3. There you can see the GM will be linearly increases with respect to VDS. After that, it will be constant. So I can say that I can say that I can say that so here I can say that so GM depends on VDS. So over here in the saturation region, or in the linear region, after when it is entering into the saturation region, GM depends upon overdrive voltage. So it's nothing but a VGS minus VTH. So as the VGS minus VTH is constant, we didn't change, so the GM will not be changed. Now what we do is, now GM times of VGS value over here, the VB value, or GM VGS minus VTH value, there at A terminal, the voltage we are trying to control now. So it will be controlling now. So let me show you how it will be done. The gate voltage which I made it constant previously. Now I will be taking multiple values 0 0.6, 0 0.7, 0 0.8, 0 0.9. Yes. So now for the different values of VGS, as I am saying, as the VGS change in the saturation region, it will be operated in the, when it is going in the saturation region, as the VGS change, as the overdrive voltage change, there is a GM also will be changed. So let me show the simulation over there. Yes, point of the GM is this one. Let me close, delete. So this is the graph for the ID change as the VGS changes, as the VGS changes. So here this VGS is 0. VGS is around 0.6. This is for 0.7. This is for 0.8. And this is for 0.9. As the voltage increases, the current value is increased. So it is not depending on VDS. When the voltage increases from this point, after that over the voltage from this one, VGS minus VTH point from this one, once the transistor is entering into the saturation, the transistor current ID, it is not depending on VDS, it is depending on VGS minus VTH. As the VGS is increasing, the current levels are increased. So this is the graph, and now even we have to prove with respect to GM changes also. So as the VGS values are changed, so here you can see the VGS value when it is 0.6, when it is 0.7, when it's 0.8, when it's 0.9. For the multiple values of VGS, the GM value level will be increased. So over here it is depending on VDS, and over here it is depending on VGS. So we wanted to clearly monitor it through the simulation. For that, what I'm trying to do is, so here whatever the simulations that I got it. So where this is the graph, initially we got it, now we are getting this kind of graph. So where GM changes with respect to VDS we are plotting. So where the x-axis is VDS and y-axis is GM, and this is the linear region, this is the saturation region. So where, let me divide this one, this is the linear region, this is the saturation region. So what is observed is, in the linear region, what is observed is, in the linear region GM is depending upon the VDS. That is okay. So over here in the saturation region, what happening is, the GM is constant with respect to changes of the VDS, but the level of the GM is depending upon VGS. So indirectly I can say that the overdrive voltage over here, if it is changed, VGS changed, the GM also raised. So now this one I have to monitor it clearly. For that, what I am trying to do is, so as these graphs are visible in the textbook, where GM is nothing but, as we know, the current equation of the of the MOSFET is of mu COX W by L into VGS minus VTH whole square. This is the current equation. So GM is nothing but derivative of GM, derivative of ID, derivative of ID, derivative of ID with respect to VGS, derivative of ID with respect to VGS. So after we do the derivative, mu COX W by L times of VGS minus VTH, I will get it. So now this is the equation where it says GM, this is the equation only satisfied in the saturation region. So when the transistor is in the saturation region, when the transistor is in the saturation region, the GM depends on overdrive voltage VGS minus VTH. As the VGS is changed, GM also will be changed. So here it is showing in the first curve equation, in the first graph, where the VGS minus VTH is changed. So here I am taking that parameter VGS on the x-axis. As the VGS change, I will be observing the GM. As VGS increases, the GM will be increased. This is the graph indicates that as the VGS increases, GM has to be increased. This is the graph. We will be simulating it now, how we extract this graph. So that it will be clearly have indication that the variations of the overdrive voltage or variations of the VGS, how it gets affected on the GM. So now the same thing will be doing the simulation. What I'm trying to do is, so as of now, where we got the plot as, VDS changes on the x-axis, ID change on the y-axis. So later on, I got the plot of GM also. After adding the SES file and all the data of GM I took, so all the operating points for which the GM change, we got it. So this is one case, this is the another case, this is the another case, like that I have all the plots. So this is the VGS 0.6, this is the level V 0.7, 0.8, 0.9, that is what the sweep values of GGS you took it. Now this is the independent variable, this is also independent variable, this is the dependent variable. So now when we have multiple independent variables, now we can hide the main independent variable and replace with the second independent variable by taking the functions. So now I will be taking the function over here, right? In the calculators we have the function. So value, I will be taking the function value of GM at VDS equal to x-axis VDS is I'm taking it is around 1.2 volts or something. So I will be plotting this one. So these values, when I'm extracting this all values of VGS of this one, VGS of this one, VGS of this one, VGS of this one. So VGS 0.6, it will be taken as a graph as VGS equal to 0.6, VGS equal to 0.7, VGS equal to 0.8. All these values will be monitored out here. 0.7, 0.8. All these values, now it will be becoming a VGS as x-axis. The corresponding GM changes, we will get it on the y-axis. As the VGS increases, the GM value increases, that we will be getting the graph like this. This is the graph it is expected out here, which is there in the textbook. So now let me do the simulation to get this graph. Now I will be going into the calculator. Let me simulate it once. Yes, now let me bring this one into the calculator. Send to the calculator. So now GM values, every value of GM I got it from this equation. So now using functions value value. So at a so the graph says at 1.2. So this is the x value. I'm trying to take it as reference. So at x equal to 1.2, all the values of VGS will be considered as the x-axis now. So this is the VDS. This is what VGS. That VGS will be coming into the x-axis. At 1.2, whatever the VGS values you took it, all that will come into the x-axis. Y values will be going into the y-axis. So now GM will be the y value, VGS will be the x value. That is how I will get a new plot. Yes. So this kind of things I'll get it on the applet. So let me bring that into the simulation window. Setup. So let me plot this one also now. So current is not required, operating point even there, I don't have a problem. Let me eliminate this one. So let me simulate that too. Yes. Yes. So here you can see at 1.2, this is my VDS, the same graph that I have copied here. So where all the values at 1.2, this is at 1.2. So all the values of VGS, this is the value, right? 0 0.4, 0 0.5, 0 0.6, all the values of VGS that I'm taking. That VGS is my variable, second independent variable. So this is first independent variable, this is my dependent variable. So now what I was doing is, my independent variable first one is going to be eliminated, this one brought it on the x-axis. So now this is my GM will be my y-axis, VGS will be my x-axis. So whatever the graph I'm expecting on the textbook, the same graph I could get it. But in the textbook it is mentioned that so approximate mass transconductance, it is not the exact conductance, it will be approximate values where I took it where I took it where I took it right, where I approximately I said that as the VGS value increases, that GM value will be increased. But the moment when you are increasing so much, let me go with the other case also. If I go with the VGS changes so much, right, as the overdrive voltage increases, the GM value will not be increased much. So let me do the simulation. So if I go with the multiple values of VGS, so let me simulate instead of set of values you given. Let me do the simulation from 0.6 to 1.5, uh, 1.5, total number of steps 10. So let me do the simulation for this one. It's not linear, Prof. It is not linear. So where you can see when the control voltage is 0.7, 0.6, VGS is 0.6, 0.7, 0.8. So like that, if you are giving, so for this range, you see the levels how it is changed linearly up to some extent. So there is no much change at a higher values of VDS, higher values of VGS. So the when we are having the overdrive voltage is maximum, I can explain you, as the overdrive voltage is increased, as the overdrive voltage is increases, so the dependency of GM will be changed, because I can say you, when the overdrive voltage VGS minus VTH, VGS minus VTH, if it is not much, overdrive voltage is not much for the low values of the overdrive voltages, what happening, the low values of overdrive voltages, so it is linear. After overdrive voltages reaches to the maximum level, right, it is not linear, right, it is trying to maintain constant, it is trying to maintain constant. So the reason for maintaining it is constant is, so as I know that id is nothing but of mu COX w into w by l into VGS minus VTH whole square, VGS minus VTH whole square. The overdrive voltage is with the square law, with the square law, the id will be changed. So when we are going to do the derivation, right, 2 will come here, so it will be function of gm will be a function of overdrive voltage VGS minus VTH. So now gm will be a function of VGS minus VTH. As the VGS minus VTH or VGS increases, the gm will be increased linearly. So this is the first case. But at a higher overdrive voltage, VGS minus VTH, if it is very high, so ID will not be a function of VGS minus VTH whole square. Overdrive square law it will miss. So square law it will be missed. So ID will be only a function of overdrive voltage, VGS minus VTH. So once you derivate it with respect to VGS, GM will be constant. So this is the reason why the GM will be constant, because of carrier velocity, it gets saturated, that mobility of the transistor. So transistor, the conductivity of the transistor, as the VGS minus VTH increases in the saturation region, the conductivity will be more. As it increases, the conductivity will be more, it will be increased. But at one point, even you increase the VGS minus VTH, the conductivity will not be increased, it will be maintained constant. So this is what a key point, that with respect to VGS, with respect to GM, transconductance of the operational transconductance of the MOSFET has to be known. So after basic concept of a transistor is known, we'll enter into the body effect. So now we'll be going with the second order effects of the MOSFET, where body effect will be the first second order effect, and we'll go with the channel length modulation, that will be second. So we'll be trying to do the simulation for these two. So coming to the body effect, as we should know about the body effect as, so as we know about the body effect as, the threshold voltage variations will be there because of the body effect. So what does it mean? So when the transistor circuit, we'll be explaining the transistor body effect first. We will discuss about the body effect first. Then we will see that in the circuits how the body effect will be having an issue, right? So first of all, what is the reason why we are getting the body effect? If the threshold voltage of the transistor when it is fabricated, we got it around 0.3 or something. If it is 0.3 or something, right? If it is 0.3 or something, it means at 0.3 voltage, so whatever the depletion region, the charge carriers that we have, charge negative charge ions that we have, it will be it will be uh, uh, forming as a inversion layer. This many charge carriers will be formed over here with the strength of 0.3. So once you give the 0.3 voltage, that will be enough to form a inversion layer. Across the inversion layer, we have the electrons channel will be formed. So once the channel is formed, there will be conduction will be started. So it means to form a channel, how much voltage is required, that is considered as the threshold voltage. So now the threshold voltage will treat it as 0.3. So now after you give the some voltage across the body terminal, so this is my transistor. If you consider, this is my body terminal, this is my gate terminal. So as of now, source, let us take it as common. Source common means the source terminal is grounded. Source terminal is grounded, and the and drain terminal is supplied with some voltage. This is my drain. Yes. So now the drain terminal has some voltage, gate terminal has some voltage, and body terminal as of now, if it is connected to this one, I don't have any problem. Body voltage is now connected with the negative voltage, let us suppose. So body voltage is connected with the negative voltage. Negative voltage. So when the body terminal is connected with the negative voltage over here, so if I'm giving minus 0.1 or something, negative voltage is given, then what happens, as of now, whatever the negative ions created up to now, because of negative voltage, there will be more number of negative ions will be left behind, because of holes are attracted towards the negative charge. So if more holes are attracted, there will be more amount of negative ions will be left over there across the channel. So now when there are more number of ions in the depletion region, the charge, this is the indication of the charge. So this is nothing but a pure depletion, right? So the depletion region where the charge amount, charge carriers, where the charge, negative ions, charge, if it is more, it will be having more threshold voltage as per this equation, right? As per the theoretical concepts, right, what we know is when the more amount of the negative charge is left behind, so to form inversion, right, to bring the electrons into that particular part to form a channel, there is a more amount of the voltage is required to get that more charge to be attracted. So it needs around 0.4. Previously 0.3, where the electrons are left over here for this part. Now this much part for which to bring the electrons over here to form a channel, more amount of the voltage is required. So 0.3 is not enough, I have to go with the 0.4. So as we observe this one, the threshold voltage previously it is 0.3 to form a channel, now it will be 0.4. So I can say that threshold voltage, as the depletion charge will be increased, threshold voltage increased. So theoretically, I can say there will be more voltage is required. We also consider as a threshold voltage. So threshold voltage will be high as you are increasing the negative charge, negative voltage across the body. So here, when you are giving more negative across the body with respect to source, then there is a phenomena happens that the VTH of the transistor will be raised. So I can say that the current across the drain terminal, as we know, the current is nothing but of mu COX W by L into VGS minus VTH whole square. So what happening here, as the VTH is raised across this one because of the body terminal is connected with the more negative voltage, right? So automatically threshold voltage will be raised. So threshold voltage raised means this whole quantity water voltage will be reduced, so that ID value of the transistor will be reduced. So I can say that when the ID current is reduced, right, we have the control totally with the gate voltage. As the gate voltage rise, the current has to be raised. Gate voltage fall, current has to fall. So that dependency now we can have with the body also. So with the body, what happening, if you are giving more negative voltage, so the current is going to be reduced. So less value of the voltage, like when we are reducing the voltage, so when you are reducing the voltage, the ID also reduced. ID also reduced. As the gate voltage you are reducing, ID is also reduced. So similar way, so how the gate is controlling the drain current, similar way my body also controlling the drain current. So I can call this one as, this is called second gate of the MOSFET. So now my concept of second gate, right? Because of the second gate, where body effect, because of the body effect, the threshold voltage of the MOSFET, because of the variations across the threshold voltage, the current will be controlled. So VGS is able to control the total current, and VTH is also controlling. So this VTH is controlled by the voltage which you are applying it over here. Source voltage is connected with the 0, body voltage is connected with the more negative. So this one will be more positive. So when VSB or body voltage over here, this VSB, the difference of the voltage, if it is changed, the threshold voltage will be changed. So as the gate voltage changed, this quantity will be varied, altered, and as the VSB changed, the VTH will be altered, that will be altered over here, that ID will be changed. So now I can say ID will be a function of VGS and also a function of VBS. Yes, so body voltage as you change, that ID will be changed, right? So it is indirectly depends on the changes of the VTH. So it is changed, the threshold voltage will be changed, so that ID will be changed. So the transistor, the conduction of the current, it is depending upon the body terminal and depending upon the gate terminal. So the threshold voltage variations mainly the basic concept of the body effect. So now we'll do the simulation now. So we make the setup here like this, and we will be changing the body voltage. So we are giving the body voltage more negative, and we will be seeing the drain current is getting fall. So as we are observing here, as the VTH is raised, as the VBS is reduced, so the total current has to be low, it has to fall. So that's what the practical way of simulating the body effect. That's what we do it in the tool. So coming to the tool, so let us simulate that. So let me close this one. Coming to body effect, schematic. Yes. So where across the body terminal, I will be changing the voltage VBS. So the maestro. Yes. So now the ID change. So ID graph itself, let me plot. Remaining, I will be make it off. So all the parameters VDS, I will be keeping it. VBS is I'm taking it as operating point, minus voltage, I'm applying it over here. So here on x-axis, I will be taking that V4 plot. V4 I'm changing from minus 1.8 to 0.3. Means V4 is nothing but the voltage of VBS. So this voltage I'm trying to change it from uh, minus where minus 1.8 to 0.3. So let me do the simulation. Yes, let me do the simulation. Yes. So there is something missed. File, this is missed. Yes. So as the yes. So this is the same graph that I have copied here. Yes. So what I'm getting is, so here here, here the VBS is the voltage on the x-axis I'm trying to plot. ID is will be the y-axis, current on y-axis I'm plotting. So as that VBS is negative, so it is going to be negative. As that VBS is negative, what happening? You try to elaborate. As the VBS is negative, here the potential is negative. So here the potential is more negative. So more threshold voltage is required to make a form a channel. So more threshold voltage is required means, so this threshold voltage, this one is more positive. So this one is more positive. So the threshold voltage is maximum. As the threshold voltage is maximum, it is becoming high, it is increasing, so the current will be decreasing. So this is the same thing happening, the current is also decreasing. So the body effect, how exactly we have the changes of the VTH with respect to the changes of the VBS. So the changes of VBS, so we got the simulations also like that. So now coming to the practical way of simulating with respect to body effect, let me take one practical example. So this is the common drain amplifier. So this is what given in the textbook, where it is in common drain amplifier where the input changes by what amount. I'm expecting the same changes at the output, just like a buffer. So this circuit, let me practically simulate it over here, but with body effect or without body effect, what will be the differences we'll try to observe. So here the current which is flowing into the output branch ID is of mu COX as it is in the saturation region, VGS minus VTH. So VGS minus VTH whole square will be the current of mu COX W by L into these all factors into VGS minus VTH whole square. So what is VGS? VGS is nothing but, yes, so we take that VG minus VS minus VTH whole square. So as that VGS value is, this is what the VG, this is what my VS. So VG minus VS is nothing but V input minus V output. V input minus V output minus threshold voltage. This is the equation that we got it for the current flow across the transistor. This is what my I1 current. So now when the same I1 current is pulled to this current source, when this current source is made constant, I have to make sure this current will be always constant. Yes. So this is the basic operation of the circuit is given. For the given circuit, I will be doing the simulation in two cases. This is the case 1, this is in case 2. Case 2. In the case 1, what I am trying to do is, I will be connecting the body terminal over here. So VB is made it as a 0 and the VS terminal is connected as output. So as the input changes, because it is common drain amplifier, as the input changes, that V output also changed. So what I'm trying to do is, I will be connecting my input like this. This is my V input. So where I'm taking the pulse and I'm changing my input with the rise time of this one. So as that input rises, right? So here the V input rises, it is almost equal to the V input. So V input rises, V output also rises, Vs also rises. So it means that the VBS of the device always it will be becoming fall. It will be reduced every time. So from t is equal to from t is equal to 0 to t is equal to 10 nanoseconds, what happening is the VBS is going to be fall. So from this point there I can observe that the VBS will be fall. Means what happening, threshold voltage of the device will be increased from this point. So I can see this is the point where there is a less threshold voltage. This is the point where I have a maximum threshold voltage. Yes. So if there is a threshold voltage will be raised, right? So there is the impact will be having on the output. So what can I say is, as the V input is raised, right? So V output also will be raised. So as the V input is raised, we expecting that the V output also rise by same amount, because it is a buffer, input and output has to be raised in equal way. So the same slope it has to be, rise of this one and rise of output should be same. So if it is raised by the 3 units, so output also raised by 3 units we are expecting. But what happening here? So because of the threshold voltage, there is a rise of a threshold voltage also. So my output cannot be raised with the same amount of the rise of V input. So there will be rise of for 2 units and there will be rise of 1 unit. So this is how my output rise right, it will be splitted by some amount with the VTH rise. So VTH is raised by some amount. So V output cannot be raised by the same amount of V input. So that's why V input is raised with the factor, with the slope, with the with the rate. At same rate, my V output is not raised. So this is my second graph with the body effect. So this is what the second graph. This is the second graph with the body effect. I got it. So with the body effect, because of rise of threshold voltage, my V output will not be raised with equal rate of my V input. So for that, what I do is I will be making my modifications in the circuit as I will be connecting my body terminal to the source. So I will be making the source equal to body. Yes. So if it is so, VBS is always made it as 0. So then the threshold voltage, whatever I got it, it will not be changed. So will not be changed. So threshold voltage will not be changed means there is no change of the threshold voltage. So as this one is constant, so as that V input raised by 3 units, so it is raised with the what rate, V output also will be raised with the same rate. So we'll be changing the V input in the similar way, V output will be changed. This is the graph with the without body effect, without body effect. So now this is how you do the connections like this. You will be getting the graph like this without doing the connection with the short the body terminal with the source terminal. You will be, so based on your requirement in your circuits, when you based on your requirement in your circuits, you have to go forward with the whatever the connections you are expecting, right? So now we can do something else to make it more clear. So I will be taking my V input minus V output on another graph. So this is what the calculator where I can get the V input minus V output. So the difference, the V input minus V output, the difference, right? It should be constant here and constant over here. So if it is 600 milli, so here also 600 milli. If it is 450 milli, so it is 450 milli at t is equal to 0, 450 milli at t is equal to 10 nano also. So this is the curve where with body effect, this is the curve where without body effect. So what happening without body effect, what happening where initially at t is equal to 0, the difference over here from the V input to the V output is maintained around 450. So here to here the difference is maintained 450. So as it is raised at is raised, V input is raised, V output is raised. So VSB is raised, the threshold voltage will be VSB will be VBS will be false. So the threshold voltage is increased. So as the threshold is increased, there is a not much rise of the V output. So that difference of the V input and V output will be increased. So it is increased, so it will be later on at a 580 or something. So this one it is going to be 580. So we are expecting the difference over here, it is constantly maintained for the input signal to the output signal. Whatever the sign you are giving over here, the same sign source signal you are expecting it over here. So the same kind of variations you are expecting here and there. So here the changes should be the same changes you are expecting. But for the different values of VTH, the difference will be at one case 450, difference of the V input to the V output will be 550 in another case. So to eliminate that with body effect, without body effect, where we observe that it will be the constant variations of V input minus V output is around 450 every time. Almost it is constant. Almost it is same. That's what we simulate it now. Practical it on the Cadence Virtuoso now. Yes. So let me go with another circuit. Let me close this one. So the body effect variations. Let me get the schematic. So I'm taking two schematics where I'm connecting constant current source. This is what my V input with body effect here. Output as with body effect over here. The same input, let me keep it over here. without body effect. So here I'm taking my input is as pulse, input is pulse, input is pulse, and 0 value is 400, 1 value is 1.8, a period I'm taking 20 nano, where I'm simulating very small range, and rise time is 10 nano. Rise time is 10 nano, and pulse period also I'm taking is 10 nano. Pulse width I'm taking is 10 nano. So when I'm doing the simulation for one simulation for 10, so simulation for 10 nano, so that is why I'm getting the simulation from 0 to 10 nano. The pulse, I'm giving the rise time of 10 nano, so it is rise from 0 level to from 0 time units to 10 nanos time units. It is only rising, there is not reaching to the maximum level. So as it is rising, that is the phase I'm expecting, so I'm doing the simulation from 0 to 10 nano. So that is what the simulation that I have done it over here. So let me do run. Yes, the same problem, same problem. I set a file. Yes, so what exactly I have explained, we got the simulations also like that. So this is the second case where I have simulated for the concept called body effect. So concept called body effect. So there will be one more effect that we have to understand. Let us go with the channel length modulation. So coming to the channel length modulation, effect of the channel length modulation, right? So as the length of the channel has the impact on the current flow across the transistor. If it is a transistor with a small channel length, there I'm taking length of the channel is L. If I'm going with the length of the channel is 2L, 3L, as the length of the channel is increased, so what I'm getting is I will be finding the R output, the resistance across the channel, right? As I can see, small signal output resistance R naught of the MOSFET in the saturation region. If it is in the linear region, we call it as a channel resistance, R on. So here I'm calling it as output resistance. So it depends on how the drain current changes with respect to VDS. So I can say that R naught is nothing but, as we know that resistance is nothing but changes of the voltage by changes of the current. So inverse 1 upon changes of the ID by changes of the VDS when the VGS is constant. So this factor where our output, what we are expecting is every time this value VDS, whenever it is changing much, whenever you are changing VDS, you are expecting ID should be constant. So for that sake, you are expecting this factor will be 0. You will be expecting this factor will be 0. So 1 upon of 0, it will be 1 by 0. You are expecting it will be infinity. So once there is no change with respect to VDS, even though you are changing the VDS. So here you are applying VDS equal to 2 volts, VDS equal to 0.3 volts, 0.5 volts, 0.8 volts, and as we are increasing the different values over here, right? So the current which is flowing should be more controlled on the gate voltage which you are applying, VGS. If it is grounded, let us suppose that VGS, whatever the VGS you change it, based on the changes itself, the current should flow. So then we can say that the gate has better control based on the gate voltage change, the current is changing. So that is the operation of voltage control current source. The behavior is more required for the linear applications like analog circuits, right? So when you are expecting my ID should be more depending on VGS and not much depending on VDS, we have to make sure the length of the device should be as maximum as possible, right? So what happening if the length of the device is maximum, So lambda will be more minimum. So channel length modulation coefficient will be minimum. So if channel length coefficient is minimum, as we know the current equation is mu COX W by L times of VGS minus VTH whole square. This is the actual current which is flowing across the transistor, right, MOSFET, as the VGS control, overdrive voltage control. So overdrive voltage, what it is changing, based on that current will be changed. It is in the saturation region, the condition is. If it is the short channel devices, there will be impact of VDS also. As the VDS change also, ID gets changed. Yes, that will be depending more on lambda. So lambda is, let us suppose 1, let us suppose VDS change will be 1 times it will be changed of ID. So if it is, you are keeping it is 0.1, means only the changes of VDS by 10% there is a change of the ID. So if you are keeping the lambda will be 0.01, means there is 1% change will be reflected over there at the ID. So now our requirement is lambda should be as minimum as possible. Minimum as possible. The channel length coefficient should be as minimum as possible, so that VDS impact on the ID will be as minimum as possible. That's what we are expecting for the analog applications. When we control the current flow based on the VGS, we are expecting, so for that lambda should be as minimum as possible, right? So lambda should be as minimum as possible. That is possible by keeping the length of the device as maximum, so that R naught will be becoming maximum. So once like R naught is maximum, I can see there is, I can say the VDS changes, much changes of the VDS will not, we cannot change the ID. So this factor will be very, very small, so that 1 upon of this factor will be very, very large, so that R naught will be very high. So R naught of this transistor, this is the small signal model of the MOSFET. So this is the small signal model of the MOSFET. R naught of this device is very, very high. It will be neglected. So this is because of the control, that drain current, right? Drain current. The drain current is controlled by the VGS. This VGS is controlling the drain current, and the drain current is also controlled by the VDS. This is the control because of the VDS, and the drain even controlled by the VBS. So because of the VBS change also, there is a threshold voltage varied. I can say this is because of the VBS. VBS changes, the threshold will be varied, so that this one will control the ID. So like that VGS also changes, so VGS can control the ID, and VDS also can control the ID. So this is the control, this is another control, this is another control. This, as this equation says, there will be 3 components I will be connecting in the small signal model. So if the R naught value, if it is very, very high, this one will be infinity if it is saying. So it will be open circuit. The device won't have channel length modulation much. So we are expecting that R naught of the device should be as maximum as possible. Then the channel length modulation will be very less. So that case, the changes of the VDS will not impact on the, will not impact the changes of the ID. So here you can observe length of the device is L and length of the device is 2L, as length of the device is increased. So from the first case to the second case, length is increased. So what happens? Length is increased means lambda value will be reduced. So as that R naught will be raised, so impact on R naught is raised. So VDS changes will not have much impact on the ID. Yes, so because the lambda value is very less, VDS changes will not have much impact on the ID. So as the VDS changes, right, ID is not changed much. So slope, you can see that slope is nothing but 1 by R. The slope is very, very minimum over here, because R naught will be maximum. So slope is nothing but 1 by R naught. So this one will be minimum. Slope is minimum over here. The slope will be maximum over here, right? So because here what happening is, this is the device where ID will be mostly controlled, right? Controlled by the VDS. So is VDS is increasing, VDS. As the VDS is raised, ID is also raised over here in this case. So ID is not much raised with the VDS changes over here in the second case, right? So now out of these two cases, which case will be more preferred is, this is the case is more preferred. So that is possible by keeping the length of the device is maximum. So let us do the simulations for this one in the practical way from the Cadence Virtuoso. So you can see that in the same chapter itself, this is about the body effect we have discussed, and this is the setup where we have created and we explained that. And now we are going with this one. So as the VDS changes because of the channel length modulation, we'll have that ID constant or is it raised? When you are keeping the different values of L, we will be simulating now. Same setup, where in the first case we have done it, the same setup, where in the first case, here with respect to VDS changes, we have plotted the GM, even we have plotted the ID also, the same setup, let me take it, so same setup. So where I'm taking the different values of length. So the length of the device I'm keeping 1 micro, maximum length we have connected. Now I will be keeping the minimum length also. So that for the two cases, let me simulate it now. Yes. So here we can see there are different plots. Yes. So here I'm keeping VGS equal to 0.4 is this plot, VGS equal to 0.4 this plot. So if you see the two plots different, this is VDS equal to 0.4, VDS equal to 0.4. Yes. So for the VDS equal to same values, so I'm expecting the VDS is same 0.4. As the VDS is raised, so this is the graph, it is also raised. It is also raised. So but here VDS is not changed, only VDS is changed. So as per the VGS change itself, it has to change. So it is happening the same. So there is no change of the ID, even the VDS is changed. So I can say that the transistor is totally being controlled by, my transistor need to be totally controlled by, my transistor need to be totally controlled by, my transistor need to be totally controlled by, so my transistor need to be totally controlled by VGS. So here as the VDS is changed, my transistor once it is enter into the saturation, this is the saturation region at VGS minus VTH, it when it enter into the saturation region, it should be maintained constant. So as the VDS rise, if it is rising like this, so this is the problem where we will be getting the VGS control is losing. So we cannot make it for the better applications when it is not better for the analog applications. So here it is happening, the length we are keeping 0.1 for this one, length we are keeping it 1 micro for this one. So here for length equal to 1 micro, length equal to 1 micro, this is for length equal to 1 micro we are getting. This is for length equal to 0.1 micro we are getting. So as the length of the device is small, as the length of the device is small, so what happening? Let us discuss. Length is small, length is small, length is reduced, lambda will be raised, R naught will be fall, so that the changes of the VDS will be more impact on the ID change. So that's why ID is going to be increased with respect to VDS change. So in the similar way, for the VGS value equal to 0.4 and VGS value equal to 0.8 also the same. This is one case and this is the second case. This is for the L equal to 0.1. This is L equal to 0. L equal to 1 micron. So over this set, as the length value is very high, we are maintaining the constant current with the variations of VDS. So here for this two set, we are not able to maintain. So this is all about the body effect. This is all about the channel length modulation. So this is all about the second chapter of your Razavi textbook. We will be going with the third chapter later on in the next video.